Hey there, I'm Zenko.dev and I'm going to show you how to make your very first PCB and schematic with KiCad or KiCad as you will call it. For those who don't know what is KiCad or KiCad, it is a free and open source software to create your schematics, PCB, and export them to various manufacturers. If you do not have KiCad and want to follow along with this video, you can hop over to www.kicad.org. Click the download button, select your operating system, in this case I'll choose Windows, and then select your server. If you already have KiCad and you want to follow along, let's go. Let's start by creating our first project. You can do this by clicking File, New Project, and then choose your project location. In this case I'll choose Documents and Board so you can follow along too, and I'll name this Tutorial PCB. Once you have done that, you'll see two files right here. There's one for the PCB schematic which ends with KiCad_PCB, and the other one which is KiCad.sch, which is your KiCad schematic file. Let's go over to KiCad.sch. This will be your appearance when using the schematic editor. You will see your top bar, your right bar, and your left bar. The top bar is used for the most crucial functions that you would do in KiCad, such as the scripting console, switching to PCB editor, filling out the schematics, and many more. On the right hand side, this is where you will do most of the things. You got select, highlighting nets, adding a symbol, adding a power symbol, adding a label, or adding a global label, hierarchical schematics, and many more. For this video, we will design your first board with this microcontroller, which is called atmega 32U4. Don't worry, it has USB HID built in, a few peripherals built in such as I2C, serial peripheral interface, UART, and many more. So if you are familiar with Arduino, then the atmega 32U4 is a go-to solution for you. Let us start by placing your first symbol. You can go to this icon right here, which looks like the gate, and you can click on it. Don't worry, this will take a while. There we go. This will be your symbol selector. You will have the filter, a list of items, your symbol, and your expected footprint. So here on the filter tab, you can type in atmega 32U4. As you can see, on this category, which is MCU_microchip_atmega, you can choose the one you like. But on this video, we will mainly focus on atmega 32U4-A. Click OK. You can start placing your first symbol anywhere you like. If a duplicate symbol is trying to be added, you can simply press escape. Now, congrats! You have placed your first symbol. We will now move on to wiring the components. So, for this, you'll need capacitors. And for that, to actually load in a capacitor, you can press C on the symbol editor once again. This time, you can choose your footprint. I'll choose 0402. It's the smallest footprint that GLC can offer. Click OK. And you can start placing your capacitors within. Don't worry, if your capacitor is C, that means it is at its default value and an undefined value. To modify these values, you can double click the C letter and then enter the capacitor value. In this case, I will choose 100 nanofarads. However, if there are more than one, and it's a pain to just rename these one by one, you can go to View, Properties Manager, select all of these components, find the one that has C, and you can rename it to the value, like here, 100 nanofarads. Now we will move on into placing the power flags. Go here, which looks like the ground symbol, to add a power symbol. In this case, we will find VCC, which is the common voltage standard for USB, which is always 5 volts. So we'll choose VCC, and we'll also need one more, which is ground. You can type this by G and D. To specify which is a ground, there's always a text that says ground with a downwards triangle. Click OK, and then place it. You can hit escape if you want. Now it is time to route your first design in the schematic. So for this, I'll go first with UVCC, which is also a 5 volt line. Don't worry, if your wire is going up into this point, it will automatically create a junction for you. So you can click here up onto the end of the third capacitor. These filled circles mean that you have created a junction, and same goes for the others. In this case, I'll hook up VCC with the same voltage line and a VCC which will directly go into the power source. If the junction here is not specified, you can click here, Add Junction. The junction symbol here will add that this AVCC line will always go into the VCC power supply. And now it is time to route the rest. You can connect here from C1 up until C3 on the other side. So here, this will be your ground terminal. So you can click here from the ground up here. This will create another junction, so that means this end of the terminal will connect to the VCC line and the other terminal will go into the ground line. Now let's repeat that process for the other symbols. So we'll choose ground up on here because it is both U ground and ground, and let's wire that in. Ground first, and there you go. This will be the full power schematic for an Atmega 32U4. Alright, now we can move on to the functionalities of our microcontroller. So in this section, you will see multiple pins, such as reset, XTL1, XTL2, these are both definition for crystal, an AREF, the VBus line, T plus and D minus, and the UCAP. Over here you'll find few peripherals that you can enjoy and use whatever you like. However, it is to be mentioned that you should read the datasheet at all times on what each pin can do. In enough talking, let us go into the routings. First up, reset. Go to the symbol selector again by pressing A, or you can click here. Now we will need a 10K resistor to pull up the reset switch. So we will place R, which is resistor, and there's no default footprint. And you can choose whatever footprint you like. So I'm going to choose 04021005 metric. In this section, you can rotate your components by pressing R. In this case, I like my component upwards or downwards, but in this case, it could be upwards. So you can click that, press escape, and do the same thing. In this case, we need 10 kilo ohms, so it's 10K. According to the datasheet and some schematics, if it's not pulled, you should pull it up to VCC, which you can click here on this power flag like I did, and then doing your usual control and copy and paste, which is Control C and Control V, of course. So in this case, we'll add reset, hook it up into the first terminal of R1, in this case right here, and you can pull it up to VCC. However, if you need a switch, you can do the same thing. So we'll go to SW_push. As you can see, there's no default footprint. You can click OK. Now, since this has no default footprint, let me press escape again. You have to double click and look for this value, footprint. Click this, and then there should be a library icon. Click the library icon, and you can go to button, switch, SMD, THD, or keyboard. Since I really like having most of components on the surface of the PCB, so I will choose SMD. There will be a huge variety of switches and buttons available for you to browse on the KiCad library. So you can take your time to browse the entire library. In this case, I'll take my time to browse the perfect push button. However, it is to be noted that you must research all components available here into your distributor site. So like for example, this 4341 switch is available on LCSC, which is a reliable source, and there are more. You can just take your time to find which button works best for you. So in this case, I will choose this one. There will always be a documentation, so you can middle click, or you can just click and you can read its documentation. Then, if you're not really sure, you can look it up. You can look up that switch and then paste it on Google and enter your sources site. In this case, I'll choose LCSC, so it's KMR to LCSC. Oopsies. In this case, it is available because we know this picture is from LCSC. So we are going ahead to use this one pole, one throw switch. So you can click OK. To save everything, you can click OK too. Now, on this end of the terminal, you should connect it to reset. For the other part of the switch, you should connect it to ground. Again, select, copy and paste, and then do your thing. And then save by clicking this icon or Ctrl S to save your changes. Now it is time to route XTLN1 and 2, which these are both crystallines. However, you need to do a little bit more research onto knowing what crystal you should use. In this case, the atmega 32.4 only needs 60 megahertz, but we don't know the load capacitor yet, so for that we have our reference schematic here, which is here. It says 22 picofarads and 22 picofarads. A good rule of thumb, while making sure, you can just go to calculator. In this case, I'll type Rechenmachine. So the standard formula for load capacitor is C1 times C2 divided by C1 plus C2. So that means we had to solve before, it's 22 picofarads. Since C1 and C2 are the same value, it is not just times 2, it's times 2. That means we need to square that. Wait, let's check again. 22 times 22, 484. Keep this number in mind as we'll be using it later on. So that means it is 484 times 22 divided by 22 plus 22, which is 44. That means it's 484 divided by 44, and you'll get that the load capacitance for the crystal is 11 picofarads. So now you can go over into your distributor site and go into the crystal section. Here you can choose crystals, either crystal oscillators, but we'll use crystals this time. However, it has to be noted that it has to be 2-pin or 4-pin if you like. So here you can set our frequency to 16 megahertz, and then the load capacitance to 11 picofarads, and you can click in stock, which are only have 3 left. You can click apply. As you can see, we have found our crystals to be this: 60 megahertz, 11 picofarads, 20 ppm. So as you can see here, it is some sort of a through hole component, and we don't want that. So you can take this, if you want, 2520 crystal, which is the same 11 picofarads. So you can pick SMD 2520 4-pin. We need a 4-pin, so that means you can hop over to symbol and then type crystal, and then we have to find ground 2. Here, I mean by ground 2 4. And based on this, we know that it's 2520. So that means no default footprint. Go here, scroll down until you find 2520, which is 2.5 by 2 millimeters. You can click OK, and the crystal will be available for you. Let's adjust this, and then bingo. Now you have to modify this value crystal, back it up like how we used to do, 16 megahertz. And you can even move your text if the space is not enough. So mine just writes 16M right here. It means 16 megahertz for space saving solution. So now we can route 1 and then 3 with the respective external inputs. So that means we route 1 and we'll route 2 with 3. We will have 2 ground terminals, but we'll ignore that just for now after we have placed our capacitors. So we need to go to capacitor. You can just do it by C, 0402. Make sure you turn on place repeated copies on so that you won't have to go back pressing A, and you click OK. Now you can spread your capacitor out just like the way how you do it. And then we'll have both of these. Go to view, properties, to set these to 22p, 22 picofarads. So that means we'll route the 3 into C4 and then 1 into C5. So again, you can copy and paste this ground terminal again, and we can route it like we used to do, and then we can press W to do wiring and attach to 4. You may notice that there's one ground terminal left, so we're gonna do this and then do this. If you don't have enough space, you can do some more allocation with you can move your components around, but in this case, since we don't have enough space and the engineers are going to be mad at the comments, so I'm gonna leave the ground how it should. So now we have completed our clock circuitry. Since we don't need AREF, you can cross that out by clicking here, add no connect flag, and clicking on the pin that you don't want it to be checked. Now I can save, and then you can copy VCC again, R to rotate, VCC. You have to connect it to VBus because that's the way it should, and then UCAP, which in order to work we need at least one microfarad. So let me type 1U there. Connect it like how it should be. And then these are differential pairs. So that for that we'll move on to the USB part. For the USB part, you can go over again, and then you can type USB underscore C underscore receptacle. Since we're only experimenting with USB 2.0, we only require 16 pins. However, the 14 pins is kind of broken, so yeah, that's a no-brainer. So we will use USB 4110. I mean USB 4. Sorry, my bad. You will use this USB 4105. So that means we go here. You can hook over VBus to VCC. However, to account that your power supply, your USB-C power supply, to be able to output 5 volts, same exact time, you're going to need 2 resistors, both of which at the same value. So to output 5 volts, you need at least 2 5.1 kilo ohm resistors. So we'll type R, 042 again, rotate, and then you can do your cleanup here. Since both the texts are overlapping, you can click R, and move into the middle so that the schematic is more readable. And you can place R2 on top of R2 and R3 below R3 itself. So we'll do that again. 5.1 kilo ohms. You have to connect these, not connected like this, as it will interrupt the signal. I mean, it will interrupt your wiring and will mess things up. You can go to ground, copy paste, and then ground. you're arriving here. For D minus and D plus, we will route it as a differential pair. So we will either need 22 or 200 ohm resistors depending on your desired impedance. So that means we will start R4 and R5. So we will start writing on D minus, which will be D minus and a D plus. So we will start creating our first label here. So you can start clicking this symbol which says add label, or you can press L for convenience. So we'll type here D plus, so KiCad will recognize it as a differential pair, and D minus. You can wire those up. For this special bus interface, you can cross them out, as we don't need that. So we can do our last routing, which is ground and shield. Both of these need to be wired into ground. So ground and then ground. Alright. Oopsies, I forgot to change the resistor, so that means we need at least 22 ohms of resistor. You can multi-select with shift, and then after that doing your normal copy paste. Since this is D plus and D minus, these match. You can make your net labels line up with the pins and it will auto connect. Stretch it out so you can make your schematic easier to read. And you are all done for the power circuitry and some of the basic circuitry like the clock. Now we will move into the functionality. For most of the board references, you can look it up online on how into routing these for the functionalities. So we will take our Arduino Leonardo. So we'll go into store.arduino.cc, and we'll jump in a schematic in a moment. For this tutorial, we will refer to the pinouts of the Arduino Leonardo, which uses the same MCU as we does, which is the atmega 32U4 in a hybrid form factor, so that we know that PC7 here, which refers to here, will be D13. Since for some of you that routing all of this is tiring, let me do the magic for you. So we'll route these based on Arduino pinouts. Alright, now I finished, and your end pinout should look like this. Now, to determine your pinouts and number of pins you want, make sure to leave some space for at least VCC, VCC, and many more. You can do this by using RX LEDs. That means we're ditching this. So we're ditching all the LEDs except D13, because D13 is another IO port, and we really need it. So that means it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So that means it is 10 per side. However, we also need to do stuff like ground, for example. So we will add another like 12. So that means we need 24 pins total. So that means in each side you'll have 12 pins. So that means you can go here and you can type con underscore 01 times 12, because we got 12 from the number we got, because we also have 10, so that means we also have to add at least 24. is again no default footprint. We have to choose our own footprint here, so we're going to choose pin header. So pin header through hole, which is 2.54 millimeters, which is the most standard for any breadboard and for any development boards out there. So you can review this first on how will be expected pin out like. If you are really sure, then you click OK. So we need 2, so that means 12 on each side. So we will start our process as of now. So we'll start with D0 because that is the most needed. D0, D1. We'll continue this with the magic of editing. We have done our design. So your design should be like this. You can copy this, pause the video if you want to copy this as your pinout. Now we'll route the LEDs. So for that, you need to make at least a kit, or that's what I call it. So you go into here, LED, no default footprint. We'll use 042s as usual, and you can use this diode polarity. So that means this will be ground, and this will be the positive terminal. However, keep in mind that you need at least 330 ohm resistors here so you can maintain the overall brightness. So that means we'll go here and press R again, and then 042. I'll do that, and then you can type here 330, and the LED color, whatever color you like. I will name it blue because it's my favorite color. So now we'll go into ground, and since we need 3 LEDs, so we have to make 3 duplicates of these. So whatever you do is select from the left as shown in this box. You can drag it along to tidy your schematic up. Control C and V, and then Control C and V again. Now you can start. I'll start with RX LED, followed by TX LED, and then the built-in LED. You can do the same technique as I did before. Merge the labels in, and then extract it out. So this will be the complete schematic. Once you have checked that there's nothing unconnected, you can check here, inspect, electrical rules checker, and then run RC. Don't worry if you got an input power pin not driven by any power pins, and you don't have anything that relates to unconnected, so that means you're good to go. So you can close the ERC, you can save it as usual, and now we'll jump in to the PCB making process. Alright, now let us start making your first PCB in KiCad at least. So you can first either go here, switch to PCB editor, or you can press F8. In this case, in my keyboard, I have to press Fn F8 because I don't have Fn locked. So for the sake of tutorial, I will not be pressing F8, but F8 is usually the key button I always use while making these type of electronics. So that means you can click here, switch to PCB editor, click it, and you have to wait because it has to import a lot of things like expand, tutorial PCB. We don't have anything here, so we can tools, update PCB from schematic. As I told you, it's F8. There are changes to be applied. Update PCB. As you can see, there are no errors and warnings, so we'll start. You can click close. Now let's start. Start by having the schematic beside you by closing in the properties manager on both sides so you can concentrate fully like I do. Here, you can match in and start your first layout. So that means I'll go with atmega 32U4, and then first C1, C1, C2, and C3. If you think, oh, this UI is distracting, you can always focus on one layer by toggling in inactive layer view mode, so you can fully concentrate on your designs. Now, you have to fully lay out. So in this case, C1 will go into 2 VCC. Be aware that these three are the coupling capacitors, so you have to place them very close within the IC. So for the next capacitor, which is on pin 14, you have to line up VCC at least correctly in a straight manner if that's possible. And then you have to go C3. C3 can go inside pin 24 like this. And I can click save. You can cross-reference your schematic and start assembling. So here we have R6, R7, and R8. We'll start first assembling it as LEDs. So that means we will do this first and find a reference for D1, D2, and D3. In this case, you can hop into a schematic editor and do your thing. However, please be noted that this is not the direction we intend for. This is reverse. So you have to press again. You can press R as usual, like in the schematic editor, until you reach your desired direction. So now you have a full kit for some of this, and you can start assembling, in which this case there's XTL1, and you need to reference those capacitors. Don't worry, you can go here and then reference those 042 resistors, and then after that you can go to XTL2. I'm going to rotate it like here, and then rotate it for the other one to have ground face upside. So you have to at least 2 capacitors, and you have to make them line up within each other. As you can see, this does not line up, so you have to route again for them to line up. As you can see, XTL2 matches and XTL1 matches too. Great. Now we can actually start doing our actual layout. So you can maximize that window and then go here, which is our UCAP capacitor, like that. Then you can start laying everything out. So like this. For reset, you need to plug it onto VCC. So here it is for reset. You can place them side by side as long as you're not following that purple line over there, which is called courtyard. And for this, we can handle over to CC1. So that means it is the charge couple. If you think the grid is not precise, you can always turn it down here. It says your grid settings, which is as of now 0.1. So you can tune it down to 0.5 for greater precision. As you can see, it's not having greater precision. However, 0.001 always works with having lots of great precision for you, so you can handle the rest. If you want these to match up, you have to overlap these, which will violate a courtyard, but hey, so you can, after that you can move the component with greater precision. So let us start actually Now we will start, since both of these are different show pairs, so we will start them. Oopsies, that's a courtyard violation. Now we'll place them side by side. Yeah, I know that's a courtyard violation, but we get the gist of it. So now we can actually start the routing. However, there are rounded rectangles that look like this in a stroke manner. So if you're not happy with that, this is called a clearance. If you're not happy with that, you can go to the board setup, which is this icon right here. You can go to net classes and make the clearance smaller. In this case, I'll set it 0.1. Click OK, and you should see that it should go smaller. So it's going to give you more space to route. So let's start with this USB-C first. We will press R to rotate, and then do thing. So we know that this is in reverse polarity, and the rest that are crossing. As you can see, the red net doesn't cross anymore. However, it will be a challenge for us to route later on. But anyways, you can design your first PCB. Yeah, anything you would. Alright. You can always use the arrow keys to move while it's in moving mode. So that means you can place this wherever you like, as long as you're not violating the courtyard. So you can start laying out your things first, like this. We'll start with VCC D0 and we'll do it with less precision because this is a header and we have to utilize the space. So we have to do like we do RR. Let's align VCC and press M. You can move your mouse anywhere, but only in a fixed direction. So for that, we'll go here, and now our layout is done. To create your first cut for the board, so the manufacturer can cut the board according to your specifications, you can go over to the edge cuts layer and choose the shape you like. In this case, I'll use a rectangle. There will always be an X and Y. X will indicate your board width and Y will indicate your board height. So in this case, we'll choose 32 out of 30 on the edge cuts layer. By default, you have at least 2 layers of copper, in which on both layers you can route. But there are more PCBs that have even more than 2 layers, such as 4-layer PCBs, 8-layer PCBs, and vice versa, and you can route them on those inner layers. Since we don't want to overcomplicate all of this, we will use 2 layers for this video. So for this, you can click here, add a fill zone, and then mark your zone. It says no net will result in isolated copper island. You have to fill it with ground because ground requires a return path. Add in your specified clearance. Before I have chosen 0.1, minimum width 0.1. This has to be your minimum width, and you can even go smaller without changing the minimum width. So that means you'll use 0.1. But these can be customized to your heart's content. So if you want 0.2 millimeter clearance, it's okay, but it's not always recommended. Also, if you want to have at least 2 layers for both of them to be ground, you don't need to even copy paste all the layers. So you can just here F copper, you can check on B on the back copper. After that, everything, hit OK, and then start marking out your zones. Here I'll lay it out like a normal rectangle, but you can always adjust your preference like this. After it's done, you can now hit B. B stands for building the copper fill. So that means we'll press B right now, fill out zones. Bingo. We can now start routing. However, you don't have any predefined width, so we can go into add predefined width. Same with board setups, predefined sizes, and tracks. We're going either for 0.1, 0.2, 0.3, and for the vias 0.5, 0.3. The reason why I'm choosing the whole as 0.3 is because we can't go any more. We can't go any more further because that'll further increase our cost. So we have to do like this. Additionally, the diameter is actually the hole plus the annular ring. So this is 0.5. We'll have an annular ring of 0.2 millimeters. And if you think 0.2 millimeters of annular ring is good for you, you should consult your manufacturer. So for example, we'll first do track 0.01 and do a normal routing. For here, you can either click this or press X. So press X here on CC1, we'll route that first, and then CC2. And for the USB pads, you can just do it rotatively. However, there is the minus, so you have to prioritize that first. So you have to do like this at least. Or if you want to, then just D plus and then D minus. However, you'll notice that it's blocking the way. So we have to reconfigure our paths. For this to be connected at least, you can always try to turn around, but it will be risky to do D minus, so we don't have anyone to have any that noise, but we're gonna do it anyways, just if you want to get started making your first PCB right here. So we'll do this, and please note that this D plus and D minus is a differential pair, so you have to hold click, and there's this text called route differential pair, or you can press 6. Number 6, you can route a differential pair, so that means this will always match the other trace's length. So you'll always keep the same integrity over time. Or you can start from the microcontroller or from the USB. I better start from the microcontroller. So we'll start. Alright, so this will create a angle section here. Once you're happy and done with that, you can press B. Fill out zones. If you want to check that the differential pair is actually on the same size, you can click here, net expector. D plus and D minus both almost have the same length as in precision of millimeters. So we'll press escape for now. Now we'll go into UCAP, but UCAP requires a different curve, so we'll use 0.2. And then for VCC, this is kind of unregulated, but for the sake of this tutorial, we'll just go with it. So that means 0.3 VCC, and then you can start routing your VCC channels. So we'll start from this part of the VCC, and then VCC again, boom, bingo, and then another VCC from this channel. But I always recommend to use thermal zones, but it's okay for those who don't know what a thermal zone is. You can just stick in with this video so you can route it with power tracks. Bingo. And we can start routing our decoupling capacitors. There we go. Once you're satisfied with that, hit escape and press B. And now we need to route all of these data pins. So we start with 0.1. As you can see here, A5, A4 all line up with the same how do I call it, with the same pinouts. So you can start routing. I'll do A5 first, and then with A5. If you think this track wiggle is bad for you, then you can just correct it out. Here we'll use A4, and then you see this wiggly trace. It's kind of annoying, but you can fix it. Yeah, and route A3. Again, that squiggly part. No, never mind. And then A2, A1. As you can see, that squiggly part's back again. Jeez. And then you can end it with A0. And press B if you're finished. You're gonna see this track right here, and we're gonna hook up VCC again. So if you want to hook up VCC, you can at least use this via by Control-Shift-V, or during routing you can press V to add a via. So we'll use that via we used, 0.5 and 0.3. We'll place a via right here. So we'll connect VCC and VCC, and then after that we can finally route. But since VCC is closed, we really don't need a via, so we can start here, 0.3, route a via, and then connect here, press B, and now we'll route everything. So we're back. Alright, now we are back with some of the core components being wired on, but we don't have this for TX LED because it is far away, and scribbling it would pretty much harm the ground plane. So we are going to teach you how to place vias correctly. So that means you have to place it correct like this. Make sure it is always close to the microcontroller, and you can start routing. It will automatically switch to the back copper here. And if you want a clear reference again, you can just toggle in inactive layer mode, and you can start your routing. So I'll place V here as the end via, and then you can repeat the whole process. So we will use D13 here, and then D13 matching with here. So we'll start again, D13. Alright, now you can route like this. Hit B again, and then you can route the rest. For some of these crossing rats nest, what you can always do is you can place vias right here, but since we have a layer underneath, we can move that by clicking on this trace and moving slightly upwards. Please note that this will make a turn which will at least disrupt the clearance. So you may need at least like this. So you could start by actually routing D0 by using a fan out. So fan out is a series of vias in a repeating pattern, so your routing is easier. So we'll start, then D11. Alright, now we have completed the wiring. If you want to see the wiring, you can just download the project files yourself, but here is our result. So you can just, oopsies, forgot about that, delete the via, and you can rebuild again. Alright, so we have to check everything if Everything's connected. You can click here, inspect, design rules checkers, and I can run DRC. Full clearance violation. This is just a pad problem, but it should be alright. And since we don't have this connected correctly, you may place it via here, so you can connect it with the rest of the ground plane and do your thing. Now let us see our results in 3D. For this, you can either use all three, or you can click the button right here. So you can just do 3D viewer. I'll click this for the sake of this tutorial, and let's see what it looks like. Alright, we made our first board, but as you notice, there are some silkscreen elements that need to be cleaned up. So let's clean it up. So you can go to up silkscreen, in reference to R2 right here. Alright, we have done with our labeling. So now let's view this again in 3D mode. Looks great, isn't it? If everything's labeled, then it would be easier for you to specify which pin is which. That's it for today. Congratulations, you have made your first PCB, and once again, sorry. Thanks for watching this video, and I hope to see you again in the next video. Bye.